Hey, so today's Leetcode challenge question is valid perfect square. It's the classic square root finding question. So we have a positive integer number and we want to write a function to determine whether this number is a perfect square or not. For the number to be a perfect square, the square root for the number has to be an integer. So as the example 1, we have 16. The square root is 4, which is an integer, so we return true. The second example, we have 14. The square root is 3 point something. It's a fraction, so we return false. So to solve this question, we can brute forcefully try every integer between 1, that's the lower bound, and upper bounded by the number itself. And for all the integers in between, we just test whether that integer square can be equal to the number itself or not. If we couldn't find one, we just return false. If we can find one, we return true. A way to speed this linear algorithm is to do binary search, because for first continuous chunk of numbers, integer numbers, the square is going to be smaller than the number itself. After a certain point, which is going to be the integer that's closest to the after the actual square root of the number, every integer after that is going to be when being squared is going to be larger than the number. So it's 0, 0, less than, less than, less than, greater than, greater than, greater than. So it's a sorted sequence of numbers, sequence there. So we can do binary search and use binary search to pin down exactly the closest integer to the actual square root of the number. And after we find that integer number, we just test whether we can recover the number by squaring that integer we find. So that's pretty much the binary search solution. So we have the upper bound and lower bound to be one and the number itself. We want to have the lower bound and upper bound to be the same, so we pin down the exact number there. We do so by utilizing the information about the middle point there. So if the middle point, when being squared, it's larger than or greater than the number, we can decrease the upper bound to be this middle point. Otherwise, we're gonna bump up the middle point, the lower bound to be middle plus 1, because in the else statement here, it's strictly less than the number, so we can safely bump the lower bound to be middle plus 1. And in the end, the lower bound and upper bound will be the same integer number, which is the integer number that's closest to the actual square root, and we're just going to test whether that number squared is equal to the number or not. So that's the binary search solution. Another solution is basically using calculus. What we want to solve here is basically a function equation, a function of x that's the x squared subtract 0, subtract a number, and we want to find the root for this question. So we basically set this to 0, we move the number towards right, and x, one of the positive root here is the for this equation is going to be the square root for the number, and we just test that x value, whether it's whether it's an integer or not. So to find this, what we can do is have a random guess about the x. So it's going to be off by a little bit. So that delta here is this h here. And what we do is by linear approximation, use a first order approximation for this formula. That's roughly equal to f of x plus the first derivative and multiply by h. So to solve this, we can solve for the h, which is going to be moved stuff towards the left, which is going to be negative f of x divided by this. So that's the formula for solving this h. That h is going to bring the random guessed x closer to the actual x. So we can use this as a recursive, like iterative improvement to get the initial random guess closer and closer and closer to the actual square root for this number. So the update rule is going to be for the next guess, it's going to be xn plus h of n, where the hn is calculated by using this formula. For our function, the first order derivative for this function is 2 multiplied by x, and the number is constant. So that's equal to negative sign x squared subtracted by the number and divide by the 2 multiplied by x. So that's the delta. In each iteration we can update the previous guess to be closer to the actual solution. So that's the Newton's method. So we're gonna just code up very quickly about this solution. The h is gonna be a function of the x. Just gonna copy this and paste over. And we're gonna actually take this to be the integer number so that we can do the same testing. And the initial guess is going to be the number, the upper bound. And we're going to do similar to this logic here. While we still, while this the squared is still larger than the number, we want to update this x to be h of x. And when we terminate it, it could be either smaller than or equal to the number. We just want to test if it's actually equal to the number. So that's the Newton's method. It's working as well. So the little bit cautious about the initial random guess. It has to be reasonable. Otherwise, you might be taking longer than it necessarily needs to, and also you might converge to, maybe coming from the negative side, and maybe converge to the, for the case, you might converge to something like -4 there, and yeah, that's pretty much it. Since that we are dealing with positive integers, that's why I put the upper bound there. It's not necessary to reduce the upper bound to be half, because everything beyond 1, we don't actually need the upper bound to be exactly as the number. We can actually reduce it to be a little bit smaller. But since we're looking at the logarithmic time, just half that is equivalent to reduce 1 iteration. It's not really any kind of a benefit, saving in time. So I don't even bother to reduce the upper bound in the initial state. So this is the solution, the binary search and Newton's method. If you forgot how to derive it, if you don't remember the formula, you can derive it by doing just a first order approximation and just solve for the delta there. So did I submit this? Try one more time. Yeah, it's working. The Newton's method code here works as well. Yeah, so that's the question for today.